Look, I need to tell you about something that happened today. And it's the kind of update that makes you pause for a moment and realize we might be watching something genuinely unprecedented unfold in real time. NASA has quietly changed the official status designation for this interstellar object. On the surface, that sounds bureaucratic, almost dull. But this is one of those moments where dry language hides a very serious shift. This is how they signal to the scientific community that what we're seeing is no longer routine. This isn't just a bright comet doing unusual comet things anymore. Something fundamental has changed, and the data has reached a point where it can't be smoothed over with cautious wording. So let me walk you through exactly what changed, why it matters, and what it may mean for where this story is headed. And before we go further, if you're following this closely, you can subscribe, turn on notifications, or hit like at any point. For the best experience, go full screen and stay with me. Up until now, the official language around this visitor had been careful but controlled. It was described as having a single nucleus, an active coma with some interesting features and measurable forces acting on it that weren't purely gravitational. But there was no confirmed fragmentation, no major structural concern, nothing that suggested the situation was unstable. Just a strange interstellar comet doing strange interstellar comet things as it prepared to leave the solar system. That language has now been revised in internal summaries circulating among observation teams. The object is officially flagged as dynamically evolving and structurally stressed with a moderate risk of future disruption. That phrase was absolutely written by scientists, choosing every word with care. But translated into plain language, it means this: the data has crossed a threshold. The numbers have moved beyond the range where this can still be treated as a quirky but fundamentally normal comet slowly calming down as it moves away from the sun. Something else is happening, and it's happening right now. So what finally triggered this change in status? What pushed the analysis over the edge? There are three main factors, and all of them came together over the last several days. Each one tells us something important about what's going on inside this ancient visitor. The first trigger is the spin. For weeks, astronomers have been tracking tiny changes in how bright this object appears over time. The technique is subtle but powerful. You collect brightness measurements over entire nights and look for repeating patterns. If an object is rotating and has an irregular shape, or regions that are brighter or darker, those variations repeat as it spins. You stack the data, test different rotation periods, and look for the one that lines everything up. Early on, when serious monitoring began, the answer was clean. One rotation period fit the data beautifully. The object was rotating at a steady, predictable rate. Then that started to change. At first, the drift was small enough to ignore. It could be blamed on measurement uncertainty or small changes in activity. But it didn't stop. It kept drifting. And today's update marks the point where that drift became impossible to dismiss. The newest light curves don't just show a slightly different rotation period. They show a rotation rate that is changing fast enough to measure from one night to the next. Think about that. We're talking about an object likely kilometers across, and its spin is accelerating so rapidly that observers can detect the change over a single day. The main brightness peak is arriving earlier each night. A secondary peak that used to be faint has grown almost as bright as the primary. And when you try to fit a single constant rotation period to all the data from the last few weeks, it fails completely. The peaks refuse to line up. The only explanation that works is that the spin rate itself is increasing, and it's increasing quickly. That alone is a serious warning sign. Objects in space don't spontaneously spin faster. Something has to apply torque. In a comet, That something is outgassing. Jets of material erupting from the surface act like uneven rocket engines. If they're not perfectly balanced, they twist the body and change its angular momentum. The fact that the spin-up is accelerating tells us those jets aren't fading. They're persistent, powerful, and still injecting energy into the rotation. The second piece of evidence is visible in the images themselves. The inner coma has changed shape. When teams compared the latest deep stacks to images from just a week or two ago, the difference was immediate. The central region where the nucleus should appear as a roughly symmetric glow no longer looks smooth or round. Instead, it's distorted and stretched, almost pinched, as if it's being pulled in opposing directions. There's a brighter concentration on one side, a dimmer lobe on the other, and a thin bridge of light connecting them. This isn't two separate objects yet. It's not a confirmed split, but it's also not the comfortable appearance of a single, solid nucleus. On top of that, faint arcs are visible in the surrounding coma. These arcs are signatures of discrete outbursts. Each one represents material ejected during a short, intense event rather than a steady flow. As that material expands outward and interacts with sunlight, it forms shell-like structures layered around the core. When you combine the distorted inner region with these burst patterns, the picture is clear. This object is not in equilibrium. It isn't gently venting material in a controlled way. It's being actively deformed, releasing material impulses as internal pressures build and release. The third trigger comes from the orbit calculations. Every new positional measurement forces a recalculation of the trajectory. For most objects, gravity dominates, and predictions become more precise over time. Comets complicate this because their jets create non-gravitational forces. Gas streaming off the surface produces a small but measurable push, so orbit models include an extra correction term to account for that thrust. If a comet's activity is declining, that non-gravitational term should shrink as the object cools. The push should weaken. That's not what's happening here. The newest orbit solution shows that the overall strength of the non-gravitational force has not decreased. It's holding steady. At the same time, the direction of that force is changing. It's rotating as different jets turn on and off across the surface. Sustained thrust combined with a shifting direction is a hallmark of instability. It means the activity pattern is evolving faster than the models expected, and the object is not settling into a stable configuration. Add these three things together: a spin rate that's accelerating, an inner structure that's stretched and asymmetric, and a self-generated thrust that remains strong while constantly changing direction. That combination describes an object under real stress. That's why the status changed. That's why the language was updated. It's important to understand what this object likely is. It's almost certainly not a solid rock. Interstellar comets like this are probably loosely bound conglomerates of ice and dust. Water ice mixed with carbon monoxide, carbon dioxide, methane, ammonia, silicate dust, and complex organics. A structure full of fractures, weak zones, and layers shaped by billions of years in interstellar space. Cosmic radiation, thermal cycling, and ancient collisions have all left their mark. When it passed perihelion months ago, the surface heated first. Ice sublimated, jets formed, and the early outbursts drew attention. But heat doesn't stop at the surface. It conducts inward over time. Even now, as the object moves away from the sun, deeper pockets of volatile ice are just reaching their activation temperatures. Material that was insulated during perihelion is now beginning to vent. Every time one of those pockets releases gas, several things happen at once. Fresh material enters the coma, a force is applied as the gas escapes, and the internal stress distribution changes. Pressure is relieved in one region while surrounding material remains stressed. Cracks adjust. Weak zone shift. Most comets survive this process, but this object has additional disadvantages. It's old. It's been damaged by eons of exposure, and it's already been heavily stressed by an unusually active perihelion passage. Now add the accelerating spin. Faster rotation means stronger centrifugal forces, especially near the equator. If the nucleus is already fractured, that force pulls harder on the weakest regions, and because the core is distorted, those forces aren't evenly distributed. Some areas are being stretched more than others. Meanwhile, jets continue to fire, changing direction and applying uneven thrust. This is exactly the combination of forces that leads to structural failure. To be clear, the updated status does not say breakup is imminent. Fragmentation has not been confirmed. The object is still intact, but the wording acknowledges something critical. We are no longer observing a stable body passively responding to solar heating. We are watching an object actively reshaping itself under stress, and its future configuration is uncertain. From here, there are two realistic paths forward. In the first, activity gradually declines. The deepest volatile pockets finish venting. Internal heat dissipates. The spin-up slows and stabilizes. The distorted core finds a new equilibrium, and the object leaves the solar system intact, forever changed but still whole. In the second, the stress continues to build. The spin accelerates further. New jets activate. Internal adjustments can't keep up. Cracks widen. Weak zones fail. At some point, the nucleus disrupts. Whether that happens suddenly or gradually, whether it breaks into a few pieces or many, can't be predicted. Every comet breaks differently. We are not there yet. This is not a breakup announcement, but today's status change is NASA's way of saying that both outcomes are now plausible. The safe, boring version of this story no longer fits the data. What we're watching instead is far more dynamic and uncertain. We're witnessing an ancient interstellar object respond in real time to the harsh environment near our sun. And the next few weeks will be critical, not just for this object, but for understanding how interstellar visitors behave when they encounter a star like ours.